Hello and welcome to this video for Chemistry 20 in the stoichiometry unit. This is Miss Simpson and today we're going to look at a continuation of stoichiometric calculations, but questions where we're given a little more information than just maybe the amount of one reactant or product and looking for another reactant or product. These questions you're commonly going to either be given the amount of both reactants or you're going to be given an initial amount of a reactant, and after the reaction has gone to completion, there's still some of that reactant left over. Okay, so that gets us into this section called limiting and excess reagents, an application of stoichiometry. So in a reaction, what happens is usually one of the reactants is fully used up. Okay, it is going to limit the reaction, or once it runs out, the reaction will stop. Okay? The other reactant is therefore left in excess. So there's more of it than you really need. So there will be some of it left over after the reaction has gone to completion, after the reaction has ended. So it's very uncommon that you have the exact amount of both reactants that you use or that actually react in the reaction. Usually one runs out first, and we call that the limiting reagent. LR, short for limiting reagent. Reagent is just another word for reactant. Okay? And the other reactant left in excess, we call the excess reagent. The limiting reagent is commonly the one that we're going to use in our calculations because it actually determines how much product is made since it's the one running out first. However, what if you're given a question like follows, where you're actually given the excess reagent information? You need to use the amount that actually reacted in your calculations. So in other words, if you're given an initial mass and a final mass, you need to find the mass change. Okay, so you have a certain amount of your reactant. After the reaction goes to completion, there's still some of it left over. The mass change is the amount that reacted, and that's what you have to use as your given mass to find your given moles. Okay, so here's an example. We have 20 grams of copper added to a beaker of silver nitrate. After the reaction ends, 5 grams of copper still remains. What is the mass of silver produced? So starting with our reaction, as always, anytime we're doing a Stoich calculation, we always want to start with a balanced chemical reaction, including states. So this is copper metal reacting with silver nitrate. Silver has a 1+, nitrate has a -1, so I just need one of each to make the charges balance. And anytime you have nitrate, just a solubility rule, nitrate is aqueous with everything. So if you see nitrate, it's aqueous. Okay? This is single replacement. So when I have an element metal, it's going to switch with the metal in the ionic compound. If it were a non-metal, it would switch with the non-metal. Okay, it's a metal, so it switches with the metal. So my silver is going to end up on its own. Now, copper is multivalent. If the question doesn't tell you what ion charge to use when you form your product, your ionic compound, you always use the first charge listed on the periodic table. For copper, that's a 2+. So I would need 2 nitrates to balance with my copper with a 2+. Again, copper with a 2+, nitrate with a -1. So I need 2 nitrates with my copper. Again, nitrate is going to be soluble with everything. Then I balance my reaction. I have 2 nitrates on my product side and only 1 nitrate in my silver nitrate. So I need to put a 2 in front of that, giving me also 2 silvers. So I need to put a 2 in front of my silver. And then the rest of my reaction, I can either leave blank or put 1s. Now, like I said, in this question, we are given the initial mass of copper of 20.0 grams. We're not being told that 20 grams of copper is reacting. That's usually what questions say when the entire amount is reacting. It's saying they're adding 20 grams of copper, but when the reaction ends, there is still 5 grams of copper left. So that's the final mass. So what we have to do again is subtract them to get the mass change. That would be 15.0 grams. That's the amount that actually reacts. Okay, so now we can use that as our given mass. And we want to find the mass of the silver produced, okay? So whenever we have, this is also known as gravimetric stoichiometry, whenever we're dealing with masses, we want to also figure out our molar masses. Copper is 63.55 grams per mole, and silver is 107.87 grams per mole. Remember, when you're finding the molar mass of a substance, you are not using balancing coefficients, okay? You're using any subscripts. There's an invisible 1 here, but you're not using balancing coefficients, all right? So now I can go to my step where I find the moles of my given with mass over molar mass. Again, I'm using the mass that reacted, the mass change, divided by 63.55. Now, I teach my students for unit analysis. The units of molar mass is grams per mole, but when you have a number or a unit in the denominator of the overall fraction, it actually moves up and becomes part of the numerator. Why that matters is because when you're looking at unit analysis, you're going to cancel any units on the top and bottom, and then the unit of what you're solving for should always be left on the top. It should always be left on the top, okay? So that's why you'll see me commonly in some other calculation questions, you'll see me commonly put grams here, grams per mole, puts the mole on the top, okay? So that we have moles on the top. Just a little side note there. So, mass over molar mass, 15 divided by 63.55 gives us an answer of 0.236. You don't have to write the entire number down, but store it in your calculator to use in the next step, which is to find the moles of my wanted. 0.236, so on, times wanted over given. In front of my wanted, there's a 2. In front of my given, there's a 1. Okay? So multiply by 2 over 1. The moles of my wanted is therefore 0.472, so on. Now I'm looking for the mass of my wanted, which I can find with moles times molar mass. So my moles, again, 0.472, unrounded, use the entire unrounded answer. 107.87 grams per mole is my molar mass. This cancels then with that because this mole is at the bottom, and I'm left with grams on top. So times 107.87 gives me an answer for my mass of 50.922 so on grams. Now I look back up the question. There's 3 sig digs in those numbers, so I can have 3 sig digs in my answer. I'm cutting off after the 9 a 2, which is not enough to round it up, so it stays 50.9 grams. When you're doing a calculation like this, always circle or put a box around your final answer also, so it's easier for your teacher to find that final answer when they're marking. Okay? So that is, again, how you do a question where you're actually given the amount of excess reagent in this question. You're told what it's starting as and what it ends as. You have to subtract to find the amount that actually reacted and use the amount that reacted. This is the amount of copper that reacted or was used up, okay? Now, what about questions, though, like I said, the other way you can see excess and limiting reagent questions, where you are given the amount of both reactants, okay? That is how you know that you have what we call a limiting reagent and excess reagent question, because you are given the amount of both reactants and you want to find the mass, usually mass, of your product. It could be concentration and all those other things that we solve for in stoichiometry, but usually it's with mass, okay? You have to determine which reactant is going to run out first, all right? And that reactant that runs out first is the limiting reagent. And again, for short, you can label that as LR because we will label that in the reaction, Okay, so the reactant that runs out first is the limiting reagent, and it is the one that is then going to determine how much products can be formed in the reaction. Okay, the other reactant is present in a greater quantity than is needed, and it is known as the excess reagent. Okay. So how do we determine which one runs out first? It's not just a matter of, let's say you're given the mass of both and looking at which one has a smaller mass. That's not actually how it works, okay? There are some steps that you have to follow. So the first couple of steps are the same for any other Stoich calculation that we've done. We start with a balanced equation. We calculate the number of moles of each reactant with either mass over molar mass, C times V, or using our gas law formula. If we rearrange that for moles, we would divide both sides by RT. So it would be N equals PV over RT. Okay, usually though it's going to be mass over molar mass. Now, this third step is a special step that you're going to do, and when we do it in the example, I'm going to do it in purple so that you can see that this is the additional step that we use for limiting and excess reagent questions. After we find the moles of each reactant, we have to even them out. Okay, because when you have a balancing coefficient in front of a reactant, not only does that tell you how many moles of it reacts, but it also tells you how many times it's reacting compared to the other reactant. So we need to even them out and look at them as if they were reacting on a 1-to-1 mole ratio, which one is actually in smaller quantity. Okay, so we do that by dividing by their balancing coefficient. The one that is then in the lowest number is the limiting reagent, okay? And so therefore the other reagent is the excess reagent. So we're going to label those. The limiting reagent is also the one that you use as you're given to go through your 4 regular Stoich steps, okay? Find the moles of your wanted. Now, you're going to use the limiting reagent's moles before you divided by the balancing coefficient, okay? That step where you divide by the balancing coefficient, step 3, is just to figure out which one again is in lowest number, which one runs out first. The actual moles that you use for step 4 is whatever you calculated in step 2, either the mass over molar mass, C times V, or PV over RT, okay? So let's look at, I think I have 3 examples of this. So starting with copper reacting with sulfur. This is a composition reaction. So copper is Cu solid. Sulfur, when it's by itself, remember, is S8, and it's a solid. This reaction is not happening in water, so I'm not using my solubility chart to find my products. It is telling me the charge of copper. Because copper, again, is multivalent, it's telling me to use the 1+ charge. Sulfide is sulfur. It has a 2 negative charge. So this would be Cu2S. And like I said, I'm not using my solubility chart. This is not happening in solution. Excuse me, this is just a solid product. Anytime you have an ionic compound, not in solution, it's solid. Now to balance this, notice how we have 8 sulfurs, so I need 8 sulfurs on my product side. That gives me 16 coppers, so I need 16 coppers on my reactant side, okay? Now, I want to find the mass of my product. That much we know. Okay, my molar mass I can find at this point. Remember, again, we don't use balancing coefficients. But we have 2 coppers, and just a little reminder on how to find molar mass of a compound. You can do this in 1 step in your calculator. Put the number of how many atoms there are of copper times the molar mass of each copper. Then add it to how many sulfurs you have, which is 1, 32.07. Okay? I don't expect my students to show me molar mass calculations in their question. They can just do it in their calculator. But it's not a bad idea to show it, especially if you're getting it commonly wrong on quizzes. You want to practice making sure you're doing your molar mass right. Always take the time to make sure you're doing that right, because you can do the entire steps wrong, just have the wrong molar mass, and therefore you get the question wrong. Okay? So that is the molar mass of copper 2 sulfide. I'm not using the balancing coefficient, just the subscripts. Okay? Now I have a mass of my copper, 80.0 grams. The molar mass, again, is just 1 copper, 63.55 grams per mole. And I'm actually going to make a little chart out of this. I also have the mass of my sulfur, 25.0 grams. I'm going to find the molar mass of it. I do have 8 sulfurs I have to add together, or put 8 times 32.07 in my calculator. Subscripts again get used in finding molar mass, not balancing coefficients. Okay? Now, this again, I should identify as a limiting and excess reagent question, because we are given the amount of both reactants. If you are given the amount of both reactants and you're not told which one fully reacts, this is a limiting reagent and excess reagent question. Okay? So after we write down all of our information, we are now going to find the moles of each of our reactants. We don't know which one's the given yet. We don't know which one runs out yet. Okay? I'm going to find moles with mass over molar mass for both. Okay? So my 80 grams divided by 63.55 grams per mole is going to give me 1.25 so on moles. And my 25 divided by 256.56 is going to give me 0.0974 moles. Okay, but like I said, there's this extra step we have to do, which is not used in subsequent calculations. It's just used to determine which one is actually in smaller quantity when we take into account the fact that copper reacts 16 times for every 1 sulfur. Okay, so I'm going to divide this moles by 16, the balancing coefficient, divide this one by 1, the balancing coefficient of the sulfur. Okay, so obviously this is going to be the same, 0.0974, but my copper, if I put that in my calculator and divide by 16, I get an answer of 0.0786. So in fact, my copper at this point is actually the smaller quantity. 0.07 is less than 0.09. So my copper is actually the limiting reagent, okay? Meaning my sulfur is the excess reagent. Now, this purple step, like I said, was just an additional step we have to do when we are given the amount of both reactants to figure out which is actually in smaller quantity and limits the reaction. The thing that you're going to do now in the next step, this becomes your given, the limiting reagent becomes your given, but you are using the moles up here as the moles of your given, not the ones down here. Okay, the ones down there, again, are just to figure out which one is in smaller quantity. Do not use it in your subsequent calculations. Okay, so you're going to take this over here to find the moles of our wanted. That is the moles of our given, unrounded again, so make sure you remember to go back in your calculator and use that unrounded answer. And now we do our wanted over given. Okay, so now we're back to our normal Stoich steps. After we find the limiting reagent, I now use the limiting reagent as my given, the moles of it before we divided by the coefficient. Now I multiply by wanted over given to find the moles of my wanted. So my wanted over given is 8 over 16. So if I take that answer again from my calculator, multiply by 8 over 16, I get an answer of my moles of my wanted being 0.629 so on moles. And I'm looking for the mass of that, so I need to take my moles, unrounded again, and multiply by my molar mass. 159.17 grams over mole. So the moles cancel and we will get left with grams. Times 159.17 gives us an answer of 100.18 so on grams. Now looking back up at the question, there are 3 digits in both of these numbers, so I need to limit my answer to 3 digits. That doesn't cut off the 0, it doesn't cut off a 5 or more, so it stays as just 100 grams. Okay? So that is how you do limiting and excess reagent questions when you're given the amount of both reactants. I have a couple other examples. They're going to be very similar, but again, just showing this extra step in purple to find out which is limiting and which is excess. Okay? So let's look at another example. You are supplied with 9 grams of potassium chloride and 6.5 grams of silver nitrate. Okay, so those are my reactants. KCl, check your solubility chart. Potassium, though, is a group 1 ion. Another solubility tip, if you ever have a group 1 ion like potassium, sodium, lithium, and so on, they are going to be aqueous with everything. Same with, like I said, nitrate. If you ever have nitrate in your compound, it is going to be aqueous with everything. This is going to be a double replacement reaction. So I'm going to produce, potassium nitrate, which again, obviously will be aqueous. Both of those are aqueous with everything. And silver chloride, that when you check your solubility chart is solid. And this is very important because it is asking for the mass of the precipitate. The precipitate is always your solid product, okay? So if you don't write your states, and if you don't write your states properly, you aren't going to know what the wanted is. So make sure you remember how to check your solubility charts, and that precipitate means the solid product. Now, I am looking for the mass of my solid product. I'm going to find the molar mass of it right now. So silver is 107.87. There's 1 silver. I'm going to add it to 1 chloride, which is 35.45. So the molar mass of that is 143.32 grams per mole. And I have the mass, again, of both reactants, 9.00 grams of KCl. I'm going to find its molar mass. Potassium is 39.10. There's 1 potassium, 1 chloride, 35.45. So that is 74.55 grams per mole. And the mass of my silver nitrate is 6.50 grams. The molar mass of my silver nitrate, that one's a little more complicated to find. Again, putting it in your calculator, you have 1 silver, which is 107.87, plus 1 nitrogen, which is 14.01, plus 3 oxygens, which are 16. You should get 169.88 grams per mole. Okay? So, again, this is a limiting and excess reagent question because I have the amount of both reactants. Okay? So, that's again how you know that you have to figure out which is limiting and which is excess. So doing that extra step. After you find the moles of each with mass over molar mass again. So I'm just going to do that right here rather than writing it out again. My N equals mass over molar mass. Now again, if I'm doing my unit analysis like I explained before, that makes this mole go up here. This mole at the bottom denominator of the denominator goes up here. So my grams cancel. You don't have to do that, but like I said, I teach it to my students that the units you want to be left with should always be on the top of the fraction. So that's why it's at the top. Okay, so this is 0.120 moles. And my silver nitrate, 6.5 divided by 169.88 is 0.0382 moles. That doesn't look like a 3 there very well. Let's make that look a little clearer. 0.038. Okay, now I have to remember, do that purple step, that extra step, where I divide by their balancing coefficients to compare them or even them out on a 1-to-1 mole ratio. Now, these are ones, but you still have to show this step, okay? 0.0382. Okay, you still have to show this step. It's marks for that step. So we now have identified, again, 0.03 is less than 0.12. So this is my limiting reagent, leaving this as my excess reagent. My limiting reagent, therefore, becomes my given. These are the moles of my given up here, not the ones after I divided by the coefficient. So I use this over here to find the moles of my wanted. Those are the moles of my given, unrounded. So go back and use that unrounded answer, times wanted over given, which in this case, again, is just 1/1. But you still have to do that calculation, showing that step, okay? So 0.0382 so on moles. Now we can find our mass with moles times molar mass. So our moles, 0.0382, and our molar mass of our precipitate was 143.32 grams over mole. So our moles cancel and we are left with grams. So times 143.32 gives us an unrounded answer first of 5.483 so on grams. Going back up at the question, again, there's 3 total digits in those masses, so I can have 3 total digits in my answer. I'm cutting off a 3, which again is not enough to round anything up, so it's 5.48 grams to the proper sig digs. Okay, put a box around your final answer, and that's it. So the only difference in this question is that it used the word precipitate, so make sure you know what that means, solid product. Okay. There's one more example, and in the next example, we're actually going to be dealing with solutions, concentration and volumes, rather than masses. It's the same steps though, okay? So I have a solution of mercury to chloride, and I'm reacting it with a solution of sodium sulfide, okay? So mercury to chloride. Mercury with a 2+ charge is what that Roman numeral means. Chloride has -1 charge. So mercury to chloride would be HgCl2. Now it's telling you it's a solution, which means it's aqueous. You can always double check with a solubility chart, but just a little hint there. Sodium sulfide would be Na2S. Again, a solution, so it's aqueous. Now, this is a double replacement reaction. So I switch my sodium and my mercury. I'm going to make sodium chloride, which is aqueous. I have to check my solubility chart, but sodium, again, is a group 1 ion. And then I'm also making mercury sulfide. Now, this is actually not on the solubility chart. I wouldn't give you a question like this, but I just know that that one is insoluble. Okay, now to balance my reaction, I need a 2 in front of my sodiums and chlorides, and then the rest of it balances. Okay, so we want to find the concentration of our sodium chloride. Now, remember our formula for concentration is N/V. So in order to find that, I need to write down my volume as well, because I'll be using that in the calculation. Now, here's the thing. I have a volume of 200 milliliters of the mercury 2 chloride and a volume of 100 milliliters of my sodium sulfide. Remember, what those volumes mean is the amount of solvent or water. Okay, you have a certain amount of those particles dissolved in that amount of water. When I mix those two solutions together, because that's what I'm doing is I'm mixing them together, I'm now going to have a total volume of solvent of 300 milliliters. Okay, so that is the volume that my products are floating around in. My reactants started in their initial volumes, but once I mix them together, my total volume that my products are floating around in is now 300 mils. Okay, so your products are always the sum of the two volumes of the reactant solutions that you're using. Now, of course, I need my volumes in liters. So 0.200 liters, 0.100 liters, 0.300 liters, okay? But just a reminder again, if you're mixing solutions, your product is the total volume of the water of the solutions. Remember, those volumes are the volumes of the water that they're dissolved in, okay? I'm also given the concentration of the mercury 2 chloride right here, moles per liter is concentration. That's 0.221 moles per liter. And I'm given the concentration here of the sodium sulfide, 0.500 moles per liter. Okay? Still though, even though we're given concentrations and volumes, it's still the same steps where I need to find the moles of each reactant, which is going to be C times V. Okay, I'm going to run out of space there, so let me actually just put the numbers in. But again, when you rearrange this formula for moles, you would multiply both sides by volume so that the volume cancels. So N equals C times V. Okay, so 0.221 mole per liter times 0.200 liters means your liters cancel and you're left with moles. So I'm doing that for both of these. 0.500 moles per liter times 0.100 liters. Our liters cancel and we're left with moles. Okay? So 0.221 times 0.2, make sure your volume again is always in liters so that the liters cancel, right? You get 0.0442 moles. And do the same for the other compound. 0.5 times 0.1 is 0.05 moles. Now, again, I am given all the information of both reactants so that I can figure out which is the limiting reagent and which is the excess reagent, okay? When you're given the full amount so that you can do the calculations to find the limiting and excess, we do this additional purple step where we divide by the balancing coefficient to figure out, even them out, to figure out which one actually runs out first. 0.04 is less than 0.05, so the mercury chloride is my limiting reagent and my sodium sulfide is my excess reagent. The limiting reagent is always the given. The moles of it before you divide it by the balancing coefficient gets used over here to find the moles of my wanted. 0.0442 times 2 over 1 for my wanted over given. So 0.0442 times 2 over 1 gives me 0.0884 moles. And now I can find my concentration with N over V. Okay, our V again of our products are floating around in 0.3 liters, both products, if I was looking for either of them. Okay, The products are always floating around in the total volume of the two solutions that you've mixed together. So our concentration is 0.2946 moles per liter. Again, go back up at the question. Leading zeros don't count, so there's 3 sig digs, 3 sig digs, 3 sig digs, 4 sig digs. The lowest is 3. So leading zeros, again, not counting. I'm going to cut it off after the 4, but that 6 will round our last digit up. So our answer will be 0.295. Don't forget your units also for concentration are moles per liter. Okay? And that is it for your limiting and excess reagent questions. Thank you very much for watching this video.